And yes, let's talk about beer. Well, in terms of Beer's Law. Now, if you Google Beer Lambert Law, you might also see it written as just Beer's Law, because sometimes it is just referred to as Beer's Law on notable websites and things like that. This is a lab technique and a way of calculating unknowns. So it's very good, useful tool. They use this for this particular part of the unit, and then we also will do a lab in kinetics where we're using the concentrations and the Beer's Law in order to figure out the rate of reaction. There is a nice video here if you need a little bit more extra. He does a really good job, and he has some good simulation that kind of shows how the photons are absorbed. So if you want to look at that, you can. As you can see here, this is a spectrophotometer, this box, and you stick the cuvettes in here. And the cuvettes are these little plastic things with the tops. And of course, we have varying concentrations because we're going to be measuring various absorbances with our spectrophotometer. Learning targets. All right, for Beer's Lambert Law, we're going to use spectroscopy to determine the concentration in a mixture of a chemical species. Going to build a calibration curve, another lab technique data analysis tool. And it's going to be created based off of serial dilution. And we're going to use that calibration curve data to calculate the concentration of an unknown. The amount of light absorbed by a solution of molecules or ions in relationship to the concentration, path length, and mole absorptivity. Explaining this is really you're explaining Beer's Law and the equation of Beer's Law. First of all, what is spectroscopy? You may have a little bit of understanding of it from Chem 1 because we talked about emission spectrums, which was these line emission spectrums in order to make the quantum mechanical model. That was some of the data and research that led to the quantum mechanical model. But basically, we talked about how electrons jump to higher energy states, and then they release the energy when they fall back to their ground state configurations. That would be line emission spectrum, like flame test kind of, data. Here we're going to be looking at the opposite, the absorption spectrum. What photons are the chemicals absorbing from the spectrum? Here, this is what they're emitting, these colors, these wavelengths. And as you can see, it's absorbing everything else but those 4 wavelengths in terms of the hydrogen there. So use of light to study matter. And it really could be any kind of electromagnetic radiation off of the electromagnetic spectrum. In our lab, we're going to be using visible light from the electromagnetic spectrum there to see what is absorbed. And from that absorbance data and using Beer's Law, we are going to be able to determine concentrations of solutions. So that's the aspect that we're going to be looking at. You can also look at different types of bonds in the compounds. Now that's more of a beyond the scope of this course and a higher level chemistry organic type class where you would be utilizing the spectroscopy data in that manner. What is a spectrophotometer? Well, it's this black box, SpectroViz. That's what I have in my classroom. They're actually quite lovely devices. It's an instrument that measures the amount of photons or the intensity of light absorbed after it passes through a sample of solution. And there's all this stuff inside the box. And we're going to take a look at a picture of what's inside there that does the measuring and detecting and all the other things. So here is the graphic of it, okay? So you have your light source and it goes through and you have like their prism and stuff right here. Then you have a wavelength selector in the slit. So you get to actually pick what wavelength of light is going to be shined onto your sample. Now you have your initial intensity, which should be 100%, of the light. Over here, though, once it crosses through this sample and goes through the sample, some of the photons will get absorbed. So you'll have less light over here. And then, of course, the calculation between the two gives you your absorbance. Now, there is a way to, hand calculate it. However, luckily with our spectrophotometers and the Logger Pro software, it does it for us. So you're looking at the before the sample, the after sample, and there's calculation involved, but it ends up giving you your absorbance value. Now, some of the photons absorbed by the analyte. Now, that's a key term. Analyte is the chemical species being studied in the lab. Sometimes it's an unknown, sometimes it's a known, but it's whatever you're studying in the lab. So some of the photons absorbed are going to pass through and get to the detector. Some of them, of course, will not be. They will be absorbed by the material in the sample or the cuvette here. This reduces, of course, the intensity of light from over here to over here, and that's why the calculation and measurement value is given. What absorbs the photons? Well, that's easy. It's going to be the electrons in the molecules, ions, or atoms. Definitely going to be those electrons. And when they absorb them, of course, it changes these values here and you get your measured value. Now, when you use a spectrophotometer, you have to set the wavelength of the maximum absorption. And you want the ideal absorption wavelength. And how do you figure that out? Well, when I go to set the spectrophotometer, I put my highest concentrated value that I'm using in there, and it generates a graph similar to this, and it shows me my peaks and valleys, and sometimes it absorbs more in, say, like red light and green light, and you might have two peaks, but you really want to go with the maximum peak. And because the spectrovises that we use are really good, it actually will assign you and tell you which is the best wavelength, the most maximum absorbance, so you don't really have to manually do that. But in AP, they will give you graphs like this and say, what is the ideal wavelength for absorption to measure this material? And here you would want to go to the highest peak, and that's how you would make your estimate for maximum absorption. Now, if I'm looking at this particular one, of course, the x-axes that I've seen in the problems in the free response usually have a little bit more detail to them, so it's easier to estimate. If I'm looking at this one, this was my estimation. I went with about 360 nanometers based off of that x-axis there. All right, so looking here and considering exercise 1, we have two absorption spectra. We have spectra A, spectra B, and we have a color wheel over here, and then we have our two solutions. We have iron 3 nitrate, and we have this iron salicylate in the beaker over here. And as you can see, they're colored solutions, as you would need a colored solution in order to do spectroscopy, of course, because it would need to be able to absorb the photons. Now, colorless solutions, they're going to go straight through. They would not be absorbing anything. Looking here, though, according to the color wheel, determine which spectrum is the correct one for the iron compound in the beaker here and for the iron compound in the bottle over here. What do we know about these, like this purple solution and this orange solution? If I see orange, what is that telling me? Is it giving off orange wavelengths or is it absorbing orange wavelengths? Yes, the reflecting or releasing, emitting the orange wavelengths. That's what we're seeing. Yes, giving off. So if you're looking at your color wheel, if it's giving off like this yellow-orange color, where is it going to be absorbing? Well, that's going to be opposite on the wheel. So over here in the blue-violet range, if it's this yellow-orangey area. So looking at that for the iron 3 nitrate, which spectrum is the better, or which one that matches the iron 3 nitrate solution based off of that idea? Yes, spectra A would be, because over here it's going to absorb better through like the 400, you know, I guess it goes all the way over here to like the 500 range, but this side of the wheel is more absorbing for the orange solution. How about for this more purpley solution, this violet purple color for the iron salicylate? That's going to be which spectrum? B, yes, where it goes mainly from like, you know, the more maximum absorptions, 550 over here to 650. Well, if you look over here from purple, you know, 550 to 650 is in this yellow-orange range of absorption. So you can identify the spectrum based off of the color wheel. It's usually the opposite side of the wheel as to where the maximum absorption is going to occur. We're looking at exercise 2, considering these two absorptions. What is the optimal wavelength? Well, once again, just read the graph. Go from the highest peak down, make your estimate. So if I was doing that for this one, I estimated it to be about 475. For the second one here, you know, I couldn't get my arrow to line up exactly in the middle, but I estimated it at 600 for the max, or the most ideal absorption wavelength. Now, calibrating it, you need to use deionized water so there aren't any particles in there to do any absorbing. You put that in the cuvette, it's called a blank, and then of course you go into the computer and you set it and calibrate it to, that's going to be what 100% transmittance looks like. The other thing you have to watch very carefully, and this is a lab error thing, is to make sure you don't get fingerprints on the outside of the cuvette. Because if you get fingerprints on the outside of the cuvette, it's going to do some of the absorbing, and that's going to throw off your data as well. So you got to make sure your cuvettes are clear. All right, so the intensity of light before and after are measured using the spectrophotometer. But like I told you, transmittance can be calculated, you know, if you get the measurements separately. The initial intensity over the intensity that of light that comes out the other side that's less, you can get your percent transmission. From the percent transmission, you can calculate the absorbance. It's the negative log of the transmittance, and that's how it's calculated. Now, if you know enough about math, you can definitely figure out where they derive these equations. However, like I said, this part's not really all that important to us because Logger Pro does these calculations for us. And in AP, they're not going to actually have you calculate this stuff. They're just going to give you data that says absorbance. So you just need to know how to use it. This is how Logger Pro looks. All right, this is how Logger Pro looks. So as you can see, it gives you the transmittance data right here and the absorbance value. So you don't have to do any of that calculating. It will be given to you. The only thing that you have to do is put in the correct concentrations, or what I will have to do. And this is called a calibration curve. The graph over here to the right, this is where I actually diluted a series of the chemical species being studied. I made different concentrations of it, and I did the dilution so I knew the exact concentration of each one. Then I could put it in here, measure the absorbance, and then I get this nice linear relationship, which is known as the calibration curve. So let's talk about what a calibration curve is. In general, it's basically a standard curve used to identify an unknown sample based off of standard samples of known substance. So you're taking, you know, an unknown and you're measuring it against ones where you've done known sample standards. How do you create it? You do a serial dilution of the chemical species you're studying. So for instance here, this chemical species we're going to be studying in our lab next class is going to be a copper solution, a copper 2 solution. So we're going to be looking at like the copper 2 ion, which happens to be a blue solution. In order to do the serial dilution, I always start with like 0.4 molar. Okay. Now, what I do for and what we do in this lab is we do a 50-50 serial dilution. Okay. What does a 50-50 mean? So say I have 10 milliliters of my 0.4 to start with. Basically, I put 5 of it in here plus 5 milliliters of water. So I take half of it, stick it in here, and then fill it the rest half with water. So now my concentration of this new one is half of what the original concentration was. This is 0.2. Do the same thing. You put 5 milliliters of that over here, add your water, 5 milliliters of water. Then you get half the concentration, which is 0.1. And then, of course, you would do it one more time and get 0.05 molar. So this is kind of the standards that I use for the copper lab, 0.4, 0.2, 0.1, and 0.05. We're using dilute ones. You don't want to get too concentrated because then the light can't get through at all and it levels off and you don't get your linear relationship. You can watch the serial dilution video if you want a little bit more information about that. It's a good video. Solution standards and the calibration curve. So here, just wanted to kind of give you a visual picture of different concentrations. Obviously, this one over here is going to absorb more light than the diluted one over here, but you want to have them at various color ranges in order to create that nice linear relationship. Okay, so more molecules in there, more particles in there, more moles in there, it's going to be more light is being absorbed. So looking here, once you get your absorbances and you know your concentrations because you created them based off of your serial dilution, you're going to create a graph. You're going to graph the concentration versus the absorbance. And of course, it's going to form this linear relationship. Now, of course, no data is perfect. As you can see here, one dot below the best fit line, one dot above the best fit line. But then you put the equation with your best fit line in here. And if it's any good, your regression line, in this case, the R squared is 0.9945. The R would be like 0.997, which is even closer to 1. You want your regression line, of course, to be 1. And I've had a few students over the years get 1.000 for their regression lines in Logger Pro, which is quite impressive, mind you. But keep that in mind. That's how you would create your calibration curve. Why is that important? Because once you do that, you get this best fit line, and we need the best fit line, that y equals mx plus b, because that's going to equate to Beer's law. And let's look at Beer's law real quick. Oh, before we get to Beer's law, in order to determine your unknown, once you've built your calibration curve, all you have to do is stick your unknown solution in a cuvette, measure the absorbance, and of course, remember your volume as to which you diluted it to before you stuck it in the cuvette. You must remember that volume because you have to use that later on to calculate moles and grams. So you must know how much you diluted it to. And in my lab, I'll be diluting it up to 100 milliliters using a 100 milliliters volumetric flask. And they're cute and they're really small. You'll get to see them. Now, Beer's law quantifies the relationship between absorbance and concentration. It follows a linear relationship when you have dilute concentrations. Like I said, you get too concentrated, it's not going to work. But this is the formula right here. A equals EBC. This is how it looks on your formula sheet. Now, sometimes on the internet, you might see it written as ABC, where A is the same thing as this E, which is the mole absorptivity constant. So if you Google around, you might see it written this way. This is how they write it on the AP exam. A, of course, is absorbance. E is the molar absorptivity constant. B is the path length of the cuvette. Now, the cuvettes standard are pretty much 1 centimeters now, but they might ask you a question where, what if they made it 2 centimeters? Most spectrophotometers, though, are 1 centimeter cuvette size, just saying. And then, of course, the C is, this is where you're going to calculate your concentration of your unknown. So the equation on the formula sheet, this one's right here. If you're looking at your formula sheet, we have molarity, we have Beer's law, we have the definition of these different terms. Also, later at the end of the lab, you'll be calculating moles and grams. So the molar mass equation, the moles equals the mass over the molar mass and so forth, will be also utilized in this lab. How does the Beer's law equate to the line on your graph, on your calibration curve? Well, A, of course, is the same as the Y. The absorbance is the Y. The mole absorptivity, and remember, the path length is usually 1 centimeter, so this value is going to be your slope. Your mole absorptivity constant is the slope. The X, of course, is going to be your concentration. And then the B should be 0 if it's perfect. Most of them are never perfect, but you shouldn't get very high y-intercept if you get one at all. But you would use that data, of course, when calculating. So, for instance, in this particular example, I've been given 75 milliliters of an unknown here with this calibration curve. Like if the calibration curve was built, it tells me the slope down here, the y-intercept. It didn't put the equation on the graph, but it told me this important information. So if I'm going to apply Beer's law here, you know, I'm going to use the y equals mx plus b form of it, okay? Like I said before, we're going to use these in order to extrapolate the information off of the calibration curve graph. So in here, I would put, you know, my absorbance, put in my slope. I want to look for the concentration, so I'm going to solve for x, and then of course I'm going to use my y-intercept here. It's a very, very small one, but still going to use it. Now I can calculate for x. And when I calculate for x, I move that over, divide, do those calculations in my calculators. I end up getting my concentration of my copper. I mean, this is cobalt, sorry. Cobalt chloride. Cobalt's a pretty like pink or red type solution, by the way. So this is how you take the calibration curve information, the absorbance of your sample, and you can figure out the concentration of your sample. So here it's more nicely written. Here's your slope, here's your y-intercept, here's the linear form of the Beer's law to use. You would plug in all that information and you would end up getting your concentration. Now let's look at calculating the moles. Okay, I know the molarity because I just calculated it. It's this number right here. My molarity, I know my milliliters, so I can change that over to liters. And now I can calculate the number of moles. Just like doing that. Use my molarity equation, or you could do the equation this way if you wanted to. I like to set it up in a T-chart, but so 0.075 times 0.01695, and here is our moles. 521 moles of cobalt. Now I can take my moles and figure out the grams if I want to. So 1 mole is like 58.93 grams of cobalt. And when we calculate that, 58.93, we're going to end up with 0. Nope, no 0. Let me erase that. Come on, there we go. 307 grams of the cobalt. So you can figure out the grams in your sample, the moles in your sample from the concentration. And that's what we're going to do on next class is we're going to be actually looking for the amount of copper in a brass sample. Brass, of course, contains copper and zinc in it. And the nice thing is the copper solutions are blue, but zinc solutions are clear. So we can definitely use this method of absorbance to measure the copper since it's the one that produces a color, whereas the zinc would not produce the color. So we're not going to be measuring the zinc at all. We're going to be measuring only the copper. So here's a nice little setup. You can check it out, be able to see that. One other thing that they might have you do is just directly use the calibration curves. Like, what is the concentration if the measured absorbance is 0.4? So really, in this case, pretend they didn't give you the calibration best fit line. Here you would just go over to the graph and draw it down, and then you do your estimation, like so. So that's another way they can ask this question. So, you know, and I kind of tried to estimate better. Like I said, this graph wasn't very good to estimate off of, but I went with about 1.7, because if this is about 1.5, that's halfway. It's a little bit to the left. I went with 1.7 times 10 to the minus 4 molar. But they could ask you to directly estimate it off the graph. Another thing they could do, this is the last problem, so I'm just going to try to get through it. If you know the concentration and you know the absorbance, they could give you a different absorbance and you have to figure out the concentration. And it's real easy actually, because all you have to do is realize that these two things are going to remain the same for both of the samples. So you can really just set it up like a ratio. So the concentration of one over its absorbance equals the concentration over the absorbance of the other one. And easily solve for the other concentration. So that's another way that they could be asking this question.